let us look out for some of the applications of op-amps. We will be first discussing about summing amplifier. Then we will do integrator circuits and then differentiator circuits. So first we will discuss about summing amplifiers. This is a circuit of summing amplifier. You have got various voltages V1, V2 and V3. You have to add these voltages and you should get your output here corresponding to the sum of the inputs. So V1, V2, V3 are the inputs and that is applied to the inverting terminal of the op-amp. This is the feedback resistor RF. So let us see what is the situation. Here you can see that I in, the input current, we have the thumb rule, I in is almost equal to IF, the feedback current. So based on this principle, we will go forward. So let us see what is the situation. We want to find out what is I in, and that should be equated to IF. I in is nothing but I1 plus I2 plus I3. Now the question is, what is I1? I1 we can write it as, what is I1? It is V1 by R1. So I1 is equal to V1 by R1. Now I2 is equal to similarly V2 by R2. Then similarly I3 is equal to V3 by R3. In fact, here we have used the concept that I1 is equal to the voltage across this resistor R1, difference in voltage by resistance. So the voltage here on the left hand side is V1 and on the right hand side it is actually VA. VA is in fact zero potential because of the virtual ground concept. So it is V1 minus 0 by R1. V1 minus 0 by R1 is the correct representation, but now we have avoided this and we have written it as V1 by R1. So hope it is clear. That is how these relations have come. So we will use these expressions for this equation. So In equals V1 by R1 plus V2 by R2 plus V3 by R3. Now we have to equate this In with If. If is the current through RF. So it is VA minus Vout by RF. So VA minus Vout by RF. But you know that VA is 0 because of the concept of virtual ground. So we will rewrite this as minus Vout by RF. So we will take this RF to this side and write this equation for Vout. So we will rewrite this out here. Vout is equal to, on rearranging, minus RF by RF into V1 by R1 plus V2 by R2 plus V3 by R3. Now, if we take for convenience R1 equals R2 equals R3 equals R, then this equation would reduce to Vout is equal to minus RF by common factor R into V1 plus V2 plus V3. So this is the general expression for output of a summing amplifier, and in this case this is a scale factor for the sum of the voltages. So, if you choose this scale factor is equal to 1, that is, if you choose RF is equal to R, then what will happen? The scale factor will go to 1 and your output would be V out is equal to minus of V1 plus V2 plus V3. So, this is a summing circuit. Of course, there will be a phase change between the input and the output. So, this is a point to be noted. V out is equal to minus of V1 plus V2 plus V3 in the case of this circuit. This is a summing circuit. If at all you want this phase change also to be avoided, you can use one more op amp just to invert the phase in the inverting mode. So, we can say that the output voltage of a summing amplifier is proportional to the negative of the algebraic sum of its input voltages. In fact, we can even convert this basic relation and circuit into an averaging amplifier if we use the scaling factor RF by R. If RF by R is equal to 1 by N, where N is the number of inputs. Here we have got 3 inputs, so you can put N as 3. So, if we choose RF by R is equal to 1 by 3, then this equation would become 1 by 3 into this. So, that would mean this is now an averaging circuit. So, if you choose RF by R is equal to 1 by N, where N is the number of inputs, then it can act as an averaging circuit also. So, now that we have discussed about the summing amplifier, the concept of averaging and so on, let us move to the next application, that is integrator. So, this is the second application, integrator. We have got a basic inverting mode of amplification of the op amp. Here, let us modify the circuit into an integrator. This is our input resistance Rin and this is our feedback resistor Rf. Now, I am going to replace this feedback element with a capacitor. So, now this has become an integrator. So, this I will call it as CF, feedback capacitor. If I call this current as In, then this current I will now name it as IC. In fact, I would prefer to denote it by small letter IC. So, In is equal to IC. I have replaced the capital letter I with small letter because you know that in the case of integration, the signal will definitely be a varying signal or an AC signal. That is why small letter I has been used. So, coming to the derivation part of it, we have the thumb rule In equals If. All the current that is flowing through this circuit will flow through this feedback component. Because of the concept of virtual ground, no current or no significant current will be flowing in. All this current will flow through this. So, In equals IC or If. I can also put it as IC in this case. So, there is no problem for In. In is equal to the voltage at this end Vin minus Va by R1. Vin minus Va by R1. But we know that Va is equal to 0. Put Va is equal to 0. So, this equation becomes V in by R1. So we have got the expression for I in. I'll write this over here. I in is equal to V in by R. Now we will try to find out what is our IC, the current through the capacitor. So in order to find this IC, let us make use of our basic concept of capacitor. We know that C is equal to Q by V, or you can write dQ by dV. And we also know that dQ is nothing but I dt by dV. In this case, I, the current through capacitor, can be given the subscript IC, and V is the voltage across this capacitor. You know, at this end the voltage is 0 because of virtual ground, and at this end it is V out. So voltage across capacitor equals 0 minus V out. So we can use that concept. So Vc is minus, there is a minus sign for this, so it is minus dV0. So from this concept we will rearrange for IC. IC will be equal to minus C into dt by, minus C dV0 by dt. So we will make use of this relation for this IC and equate it to this I in. So let us move this. So I in equals V in by R, that is equal to IC is minus C dV0 by dt. So that dV0 by dt, that is equal to minus 1 by RC into V in. So this is a final expression. You can see that the rate of change of output voltage is equal to minus 1 by RC V in. So let us integrate this equation and get an expression for V out. So V out is equal to integral of dV0 by dt, and that will be equal to minus 1 by RC integral of V in dt, the limit being 0 to t. So finally the output voltage V out is equal to minus 1 by RC integral 0 to t V in dt. So you can see that the output voltage is proportional to the integral of the input voltage. So this is one of the most important application of op-amp, how op-amp acts as an integrator. So we'll just brush up once again. Here what we have done is the feedback component RF was replaced by CF. So we replaced the direct current capital I with the alternating or varying current small ic. We got an expression for IC that we started from the basic concept that C is equal to dQ by dt. Then we substituted for Q in terms of current and finally got the expression for IC as minus C dV0 by dt. So equating IN equals IC, we got this expression, rearranged it and integrated it to see that the output voltage is proportional to the integral of the input voltage. So this is how an integrator works. In fact, I left out the equivalent circuit of this integrator. This thick arrow shows the concept of virtual ground. So A is a virtual ground point. This is a R1. This is our CF. This is the input V in, and this is the output V out. So equivalent circuit of this integrator can be drawn like this. Now let us do a mathematical numerical problem. If our R is 1 mego, and capacitor is 1 microfarad, and our input voltage is equal to 1 volt, let us see what will be our output voltage. We have the equation V out is equal to minus 1 by RC integral V in dt. So let us substitute the values. R is 1 mego, C is 1 microfarad. So V out would be minus the constant value, or the scale factor would be minus 1 from this. So minus 1 or minus 1 integral V in dt. So as said, since this is a constant DC input voltage, the output will be a ramp with a slope given by minus 1. Slope will be minus 1 for this output. Now let us take another example. What if our input voltage is A sin omega t? We know V out is equal to minus 1 by RC integral 0 to t V in dt. So this is our V in. Substitute it over here. Okay, there is a minus sign. Now integral of A is a constant, you can take out. Integral of sin omega t is cos omega t by omega. So this will be our final output voltage. A by omega RC cos omega t. So whatever is the constant, you substitute it and you will get omega is the frequency of the input signal. So substitute it, you will get the final output value. So before we conclude this integrator circuit, let us just sum up. The output voltage will be proportional to the integral of the input voltage, and there will be a scaling factor of minus 1 by RC. The integration will depend on the time 0 to t. So coming to the input signal of a DC voltage, this is a DC voltage, it remains constant with respect to time. If this is the input here, then what will be the output? So you can see that this is a constant voltage. So it will come out as if you integrate a constant voltage V in. So you will get a ramp voltage like this. This negative ramp is because of this negative sign. So this will be the output. With respect to time, it will go on increasing in the negative direction. That is what this equation suggests. Now if the input voltage is a square wave like this, what do you expect for the output? This is a constant positive voltage, this portion. So you will get a negative ramp like this. Now from point here to here, it is a negative constant voltage. So the negative voltage will appear as a positive ramp here. So it will have a positive slope. From here to here, then it is again positive, so it will have a negative ramp here. So for an input square wave, you can expect a triangular wave like this. Now let us take the example of a sine wave input. So if you integrate a sine wave, you will get a minus cos. So minus cos plus again this minus sign is there. So it becomes positive. So the integral of sine would become in the final output as cos wave like this. So these are the examples of input and outputs for a integrator circuit. Now let us try another application of op-amp. Third application, differentiator. This is an integrator circuit, so let us convert that into a differentiator. So what I am doing is remove this resistor and make it a capacitor then. Now replace this capacitor with a resistor. So I'll call this RF, feedback resistor. This is capacitor C in, input capacitor. So what we have done is we replaced or exchanged the positions of capacitor and resistor in order to make an integrator into a differentiator. So now we will replace this feedback current IF with a subscript IR because it is a current through resistor. So it is IR. Now this input current I in can be replaced by the subscript IC because it is the current through the capacitor. So our thumb rule, I in equals IF can be replaced as IC equals IR. Now let us see the equivalent circuit. So this is a capacitor. You can call it IC or I in. This is the current IR. This is a resistor. This point is a point, that is our virtual ground point, AB. This is the input signal, this is the output signal. So this is the equivalent circuit of a differentiator. Now let us try to evaluate the expression for the output of the voltage. So we will evaluate IC equals IR. IC equals IR. First let us find out what is IC. When we did integrator, we found that IC is equal to C dV by dt, where V is the voltage across this capacitor. So let us see what is the voltage across this capacitor. VC, voltage across capacitor equals V in minus VA. But you know that VA is 0 because of virtual ground. So VC is nothing but V in. So this VC we will replace as C. VC is nothing but V in. So dV in by dt. So this is an expression for current through a capacitor in this case. Now let us evaluate what is IR, current through the resistor R. IR is equal to VA minus Vout by RF. Current is voltage by resistance, VA minus Vout by RF. So it is VA minus Vout by RF. But you know that VA is 0. Virtual ground. So this becomes minus V0 by RF. So this is the expression for IR, this is the expression for IC. Now we will equate it over here. So we will put it here, minus V0 by RF is equal to CV in C dV in by dt. So we will rearrange this equation to get V out. V out is equal to minus RC dV in by dt. So this is the final expression for output of a differentiator. So output voltage is proportional to the differential of the input voltage, and the scaling factor here is minus RC. Now let us take an example. Input voltage is a constant DC voltage. It's a constant DC voltage with respect to time. So what do you think will be the output? See this equation. V out is equal to dV in by dt. So what is the differential of a constant voltage? A constant. It does not vary with time, so the output will be 0. So you will not get an output will be nil. You won't have any output signal. So this is very important. A constant DC voltage will give a 0 output for a differentiator. Now let us see another example. What if our input is a square wave like this? So this is a constant voltage, so your output will be 0. The input is a constant voltage, so the output is going to be constant. Now the input falls suddenly. So this varying signal will appear as a ramp here. This is a falling voltage, but it will appear as a positive ramp because of this negative sign. So this will appear as a ramp over here. It's a constant voltage, so your output will go to 0. But that fall of capacitor voltage will appear like this. So this will appear somewhat like a spike. It will remain 0 till this moment. So that is this portion, it will remain 0. Then from here onwards, you can see that it increases sharply. So there is a dV in by dt. So it will appear as a ramp voltage. Then it will again fall off suddenly to a constant voltage. So finally what you get is something like a spike at the output. So the first part is an increase at time 0 from 0 voltage to a maximum constant voltage. So this part will appear as a fall voltage here. Now at time 1 there is a sudden fall. It will appear as a positive spike. Then it remains constant at 0. So there is a sudden fall of voltage and it remains at 0 till the point 2. This is a point 2. Then there is a sudden rise at 2. It will appear as a negative rise here. Then it remains constant at a high voltage. So the output will go to 0 here. And finally at a point 3, this would be the situation. So for an input voltage of this shape, your output is going to be spike voltage like this. So a square wave converts into a spike wave with the help of a differentiator. So with this concept of integrator and differentiator, we can do many numerical problems, and you can refer your textbook with this background of theory.